I give the floor. To Stanislav Kaniukov, representing PrimeGroup. He will follow up on the subject that we started.
Hello, my name is Stanislav Kaniukov, PrimeGroup. I will speak about which is a logical continuation of the previous presentation on application of radar images on radar interferometry, and together with Alexander, we'll be showing a couple of same slides. Sorry for that in advance. One comes from another, actually. I'm not going to speak about my company, just that this year we celebrated our 20th anniversary. We've been doing space imagery from 2003, and in the past 5 years we've been recognized as best partners as leading Earth remote sensing data, and this year summer we became members of the club of interferometry players. Now we do interferometry monitoring of oil and gas fields and the scientific endeavors that Alexander mentioned in his presentation. I will speak about practices and practical results. How do I page through this? Now I get it. Here we have a selection of radar satellites. Their number are much fewer because there are hundreds of different optical satellites. Radar satellites are more technologically advanced and sophisticated. Only the best companies know how to build them. And the only thing that we have to be mindful is that imaging has been done since a long time already, and the huge archive for the whole area of globe is accumulated that people can use for their studies. What interesting things have happened, which is a launch of a new satellite constellation from Maxar Technologies and Passer from Airbus Defence and Space that we put a lot of hope on, that potentially can help us in getting high quality data in future. INSAR technology, very easily interferometry plus synthesis aperture radar. It shows a schematically shows the procedure of how information change detection is done or shift measurement is done. Our radar is active. It shows the electromagnetic impulse to the surface of the Earth, receives the reflected signal, and measures the temporal difference between the beginning of the signal and its acquisition. So when moving again over the same place in the orbit, they do the acquisition again. If the temporal shift is different, then we understand that there might have been changes on the surface. So in theory, even by two different values, we can measure the difference, but it will be too rough a measurement to get more or less precise or accurate information. You need to do multiple imaging. So the more revisit time, the more information we'll get about the changes or shifts on the Earth's surface. And in terms of the number of, based on the combination of these radar images, we build the map of the Earth's surface with the points. Each point is a constant reflector on this Earth's surface. For convenience of visualization, usually this thing is painted into colors. It is not regulated. It's up to the implementer to paint it different colors. For instance, blue points are the parts of the surface which are rising up, red who are going down, yellow which do not change their positioning. And at which point we can get the separate diagram of how this point shifts, where each time after acquisition it gives you different values. A lot of advantages of this technology. First, historical studies which cannot be acquired through the optical band or range. Whenever we do some design work before construction of a big site, we can take the data from the past, accumulate it from the past, process them, and identify unstable or potentially hazardous areas for, say, construction, where construction is not advised. Another important thing would be the additional measurement device. We're not, of course, replacing the traditional surveying geodesic method. This is simply an additional information that helps us better understand what's happening on the surface. At the same time, we can achieve high density of points on surface. For instance, for highly urbanized or industrial areas, we're talking about tens of thousands points of reflection. So for a big area, we have a colossal mass of information that we can use. At the same time, the precision is astounding. We're talking about hundreds of thousands of points, and the achievable precision value is up to 3 millimeters for each point that we can follow. And we can also see the annual gradient up to 1 millimeter per year. Of course, we can go into below 1 millimeter, but as long as we also have economic parameters to consider, there's always a compromise between the number of images in the series and the accuracy that customer is ready to accept. High revisit time. We have imaging systems which can monitor every 4 days the areas of our interest. A bit later I will tell you more about it. And again, the main advantage of the space imagery is global coverage. We don't need any permits, as with aerial photography or laser photography. We work all over the world. We have archives of data. Radar images are traditionally big, 30 by 50 centimeter. 30 by 50 kilometers is the main format, and the whole territory is covered by this data, and we can use it. And the biggest advantage is economic efficiency. We get many points of measurements, high precision for a large area. Of course, no surveying methods are capable of doing the same, because to send so many people to install markers would be too difficult and too costly, and the main task of interferometry to find a problematic spot, and then on this spot traditional methods of observation will be concentrated to continue working on this problematic area. There are many advantages, but the situation is not so simple as it sounds. Why? Because what a customer does when he gets interferometry data, of course he takes land data and compares calculated and measured data. And unfortunately, there were a number of projects where these values did not comply, did not coincide, and there was some opinion among mark shaders. There are two camps of those who are advocates of interferometry and those who are totally against it. We have tried to look at it, why there is so much inconsistency, and there are things among our implementers, problems with algorithm of processing, problems with the qualification of users, and the wrong planning and organization of the interferometry projects for the customer. What work stages should we be mindful of? The preliminary stage is very important, when we need to analyze the actual location or venue in terms of physical and geographical capacities. We need to understand and acquire information and analyze information about the observation site, and endorse with the customer what kind of parameters they are looking at. After that, we organize the actual image acquisition, analyze the capacities of the imaging systems, so that we select the types of data needed for a particular task, and we do the acquisition. And the final stage, we do the processing, interferometric processing, and we show the customer the vertical shifts on the objects of infrastructure located in the zone of interest. We work so historically it happened that most of our customers are in the oil and gas sector and in Arctic regions. The particularity of that region is active geological processes. These are permafrost areas which has certain nuances on the processing. Snowbound season, our working months are June, July, August, September, when there is no snow. Hydrographic layer is too big, also full of snow. When there is a snow melt, the areas are inundated and it's quite critical. And again, 3 months season is getting narrower because of the flooding period. So we're talking about 2.5 months best to do the actual acquisition. And different atmospheric phenomena, interferometric distortions that can affect the data, especially it's critical for L band and for LS satellite. About 30% of all data have to be rejected because of the anomalous phase interference. Whenever we select data, we need to be mindful of the following indicators: wavelength, and the shorter the band is, the more precise the measurements are, but they're most critical for the quality of image acquisition, and there might be some loss of coherence. Resolution of data. We have difference from 1 to 30 meters, and our recommendation for the infrastructure facilities to use data from 1 to 3 meter, because we'll have to connect the acquired points to specific locations, and highly detailed data are critical here. For the model, you can get up to 30 meter data. Again, broad swath, that's also an advantage. And most of the oil or gas fields are covered by a single frame of 30 by 50 kilometers, which is great. Allows our customers to buy less materials. And the period of image acquisition, as I told you, it's 2.5 months. Within this period, we need to get enough stacks of at least 15 frames, and the period of interferometry image acquisition is important here. We have used the data from 2 systems this season: Cosmos SkyMed system from Egeos and Terasar tandem data from Airbus. Egeos had problems. Out of 18 images and the imaging plan, they had to cancel 5 image acquisitions. We had to reschedule it again with the customer, and until the very end, until the end of October, we didn't know whether we'll get the data before the snowfall or not. With Airbus, everything was good. We had initially endorsed schedule. It worked day to day. I would like to thank Fabrice for that. Thank you, Airbus. Why I mentioned the satellite pass, because 3 Airbus satellites can do 7-day cycle, which is very important, and we have stable data with high quality acquisition with a short period of time to get enough interferometry stack of images. Very important indicator is inundation. As I mentioned, any water or inundation in the gas and oil fields make our lives much more difficult. Here we either use more longer wave data, which keep the coherence, but then we'll lose in the quality of measurement. So it must be taken in consideration, and you have to plan for it when you plan for acquisition. Vegetation. It does affect it, but if there are trees and shrubs, of course it can affect the quality of the image. We were lucky. It was tundra, and we didn't take it under advisement. But again, either we use L-band data, which are reflected from the Earth's surface, and go through the canopy. This is the only option, I think, when you do forest monitoring, because L-band will never give you high-quality data. And the problem with the snow cover. Again, we can say that one can use L-band data, which in theory can go through snow, but in practice it doesn't work so easily, because if the snow had just fallen, it's too fresh, the signal will go through this and will be reflected from the Earth's surface, but the snow melts, new snow falls, and in fact any snow is like layer cake made of ice, snow, different layers, and dirt also, and the quality of data is going down drastically. So you have to be very careful about how to use this data. For X and C bands, we offer to use corner reflectors. There are things, the problems with that. There could be wet snow, so it's like huge plexiglass triangular thing. But whenever it's covered by snow, we lose the data. Specialists from the Mach Shader service and their surveyors don't want to brush up those facilities. Why? Because they're located high up and it's simply dangerous. And secondly, because people have many other things to do, and to do this sweeping is not up to them. So we have very few, or I'm unaware actually of any monitoring jobs in wintertime. So we did two tasks of biodynamic monitoring, of looking at the shift of the surface of the oil or gas field. It's an important parameter after a few years in the beginning of the development of the area. There might be subsidence, and the area might subside. And also another type of monitoring which is more critical, because these are technological facilities we're talking about, and when everything goes down, it's not so dangerous when different things go down differently. When one angle is stable, another goes down, there might be a breakup point, which means that there will be an emergency at the oil field. For dynamic monitoring, we use Sentinel data. These are free of charge data, but still we believe that they must be used, which allows us to get information in C-band on the territory located beyond the production complex. For geotechnical monitoring, we have used Cosmos Sky Med data. You can see the differences in the density of points. Coherence is getting lost in X-band, and whenever we have inundated hydrography and vegetation, we have no data, but the rocky outcrops and infrastructure shows high-quality data. After visualization, we put it superimposed it on the space image. And in conclusion, this is the slide with our recommendations how to use the two systems. Only two systems for Arctic region. This is Cosmos Sky Met. All 4 satellites must be used actually, and 3 satellites from Airbus. We simply must approve the schedule of image acquisition with the customer, because almost all major companies have their own meteorological stations, and they can give you accurate information about the snow melt whenever there is a snowfall or flooding situation, and helps actively use this very narrow windows for high quality image acquisition. Minimal package of interferometry package that needs to be used for technical monitoring would be 15 images, and optimally it's better to focus on 20 to 25 images depending on the budget, because some of the images might be rejected anyway. We need to actively use the Sentinel data, because this is a free of charge satellite. We won't be able to complain about this, of course, but this year we encountered one fact which we cannot explain. Whereas originally we got 8 images every acquisition season, this year we hardly got 5 in the area located not far from Yamal and Bedan. To the south of it, the periodicity remains the same statistically, but in northern area this year there was a gap which we cannot explain. And naturally, what can we tell the customer? You wanted 8, unfortunately you get only 5. And this is quite a high accuracy, down to 4 millimeter accuracy, many points for a huge area, which is perfect. And I think as the algorithms are becoming better, Alexander Dmitrich mentioned that while methods of constant reflectors from Airbus are being tested, but we're waiting for them to be introduced, and we'll happily use those algorithms for calculation. It would be great if in Russia we could have this good INSAR products. Thank you. Hopefully I was within my time. Yes.